a fresh recording. Okay, so we're gonna look at network technology basics. Just want to double check if everything is connected. Right. Okay. So let's get to my cursor. Okay. So no, I didn't take screenshots yet. I'll do it after this quick session, not yet. Because everybody obviously had that introduction to the competition now. And I thought I'll do it when I'm done with this first slides, when these one, because there's I think three sections I want to cover. But yeah, we'll do the screenshots when I'm done with this particular section of the short course. Right. So with regards to network technology basics, we are going to look at how does the network really work in cloud computing, and what's the basics of networking. Also look at switching and routing and certain things that you would configure in a data center for your network to work. So these are the basis of how interconnection and all the platforms all work together. And you need to understand that the whole thing of the network being responsible for us, receiving information is very important. And so we need to understand, how to classify certain networks by subnetting IP addresses. So we'll go through that. We'll also understand what's the principles of the communication, of how communication flow from source to destination. And then for you to familiarize yourself with principles of how switches and routers work, and then understand the principles of basic configurations of a VLAN. So what is a VLAN? A VLAN we'll learn later on in the course. That is basically just a virtual local area network that you're creating. And so let's say you want to have HR department here. So I'm just call this HR. And you have, let's say IT. All right. And you maybe have your data center. So this is DC stands for data center. You want to make sure that HR don't see the traffic of IT don't see the traffic of the DC and so forth. So you would create a VLAN. So you would say the VLAN ID here for HR might be, let's say, let's make it 20. And then you have IT's VLAN ID would be 30. And then the data center would be 10. So you would just say VLAN ID 10. So what that means is that you have control over security of what happens on the switches, because VLANs work with switches, and we'll go through that in detail during the course. But I thought I just want to show you basically what is a VLAN and why you do subnetting, because the subnetting talks about how you would create these VLANs based on your subnetting, and how you want to have usable hosts for a certain subnet, how many hosts you want to have available, so that you don't let's say, create a subnet and then you don't have unutilized host on that subnet. So you don't want that. So that's basically where the whole thing of VLANs comes into play. So we're going to go through the basics first. So the basic is basically what's an IP address. And so an IP address is basically a identity that you give a router on a network or on a cloud. That IP address allows the device, whoever gets an IP address, to send and receive data packets on a network. And so in this case here, you would have the data sitting here, and the data needs to get, maybe to this router here. And so what it needs to do is it will need to find by each router, what's the next router's IP address. And that's normally what they would call neighboring routers. So you would find what's the neighboring router's IP address, and you would provide it to IP1 and so forth. Because the the network can't do a guessing game. It can't guess. It needs to then get information from the neighboring routers in order to send the IP address to this router here, which is where the fifth IP stopped. So normally we would call this hop count in network terms. And then so the hop count is basically you doing a trace route, and then it goes from this particular destination to the end. So the routers does that in the back end. They do all the processing, and they try to really find out where the packet needs to go to. So what an IP address is, it's a real world IP address and address, and it identifies where on the network that node or particular device is to the source and destination. And so when you look at it from I'm just going to see if I can run a trace route just to give you um, that perspective. Let me just see if I can bring it up. I think I have to. Oh, there we go. So I'm gonna just try to open up a terminal, and just to give you the whole thing of what it looks like. So I'm gonna use this local terminal. Hopefully you can see my screen. Just make this bigger. Right. So what I'm saying by that is that you would do a trace route. So it's trace route. And then let's say the website we want to look at is let's say google.com, google.co.za, right, google.com. So what will happen is if I enter now, you will see that it's going through the network, and this numbers here, the hop count, will basically represent how it's going through the next router. So currently now it's trying to get to google.com, which is in this case maybe this IP here, IP5. Just make an example. And so what you can see now, basically what happened is that it went from my home router, which is a 192 local router. Then it went to my service provider, which is FreeHost. And so it obviously went to that IP from the FreeHost IP. And then again, it went through another router in FreeHost, another router, another, like three routers it goes through, actually four. Then from there, it goes out on a gateway through their particular probably gateway, DC2. You can see I think D2C probably means data center. And then after that, it goes to traverse through all these routers in order to get, if you look at the bottom here, to get to Google, which I think it's this one here. No, I don't think that's Google. It's probably here. Here's Google. There's the N. I'm not sure what it's actually traversing here, what's happening on this side. But again, that's how you would kind of ping to find out or trace it out to get to the source and destination. So this numbers that you see here, it's the hop count. It's this hop count that you see here, which is first hop, one, two, maybe here, three, four, and then that's the last hop. So that's the destination that is there. And so your hop count can be longer, but I think there's a maximum of 15 hop counts. So let's say I Google, not Google, I go and let me just clear the screen. Um, sorry. Right, so let's say I do a trace route, and I say, can't think of something now. Let's say I say, I can't think of what. Okay, let's say Facebook, for instance. So let's say www dot, well, let's try an IP, but we'll see. We'll see now. Facebook.com. So what will happen is again, we'll go through my home router, try to get to the Facebook domain, which is this here. And it's going to basically go through that hops again. I think the maximum hops is 64 hops that it can go through. And that's basically just trying to find, can it get to the source and destination? So you can see there, at 15 hop count, it went to Joburg. And then from Joburg, it went through a different other routers. And at the end of the day, it's still going to get to Facebook. At 18 hop counts, it's doing something. So again, that's basically how you can get, to the destination. So let's say you needed to get to your host provider, which I think I'll just use this one here, which is the number 8. You see it's still trying to trace it out. Now when you see these stars, that is firewall. The firewall is saying, wait, you're not allowed to do any ping or trace route packets on my network. I will stop you right there. You can go via HTTP, that's allowed, but firewalls normally would kick in, and then you have this problem. So we're just going to ignore that. So we're just going to clear, and we'll do trace route again, and this time we'll use the IP address that I got, and so that will go to the amount of hops that I will get to that destination IP there. And that could be, in this case, this example that I'm showing here. The router does this automatically, it does this whole trace route, it does the ping in the back end. It's trying just to find the device. And you can see there I got to 8 hops to get to that device. So that successfully means that I can get to that host there on the network. Now, if you needed to know more information, you can use Wireshark, and then you can get more information out from doing this trace route. and that you can see in Wiresock. All right. So that's basically what I just wanted to show you with regards to how you get an IP address and how you define how the router see IP addresses on the network. So an IP address format normally would be seen as 32 bits. And what we mean by 32 bits, it means that we have in binary, normally we would see this as bits, right? So these are all your bits. Ones and zeros, it still adds as a bit, but you would have 32 bits in total. So what happens is that each octet that you see you have eight in total, right? So you have eight there, you have 8 there, and you have 8 there, right? When you add it all up, you should get to 32 bits. Okay. Now, what happens is that you basically have the PC that has an IP address, which you can see here, and that IP address needs to be converted to binary. So that is decimal to binary. And so what happens is that you need to understand this particular table. This table here is like almost like a Bible in networking. It tells you um, to the power of 2, which is base 2, how you have to work out the IP address from conversion from binary to decimal. So if you have these values, always would always be the same, and this will always be the same, right? And so what happens is that if you need to work out 192.168.10.1, you basically use this table, and at the bottom you would create a blank table like this, and then you would say, can 128, if you add 128, is it less than 192? Yes, and then that becomes a 1, right? So then 128 is part of your calculation to do the conversion. Then you go to, and then you obviously write the binary notation, which is obviously 1, 1, because 1, 1 here gives you 128. No, it's actually not 128. 128 plus 64 gives you 192. But if you have to work it out, you basically have to use this table as your guidance in order for you to get to understand how many bits you will get, because 128, and if you obviously subtract 128 from 92, you have a remainder of 64, and then you would do that, and then you would have nothing left, and then the rest becomes zeros. So that's how you work it out from decimal to binary. But if you have the binary numbers, you just basically take that binary digit, throw it here in the table, and then it will give you the values to decimal. So if I had to work out 168, then what I will do is I'll basically have the table, and I'll just draw, I think, 8 blocks here. 1, 2, 3, 4, 5, 6. I think that's 8, 2, 4, 6. Now there's one more left. See if I can squeeze in. You see? 1, 2, 3, 4, 5, 6, 7. Now it's 8. I counted wrong. Okay, so now what you will see is, let's say we want to work out 168. So we want to work out the decimal of 168. What we'll do is we'll go through this and we'll do the kind of subtraction. So you would say 168, 128, can it go into 128 into that, right? You will say yes, because 128 is less than that. But now you have 64, right? And now 64 would be obviously a problem, because now you obviously have to think about, okay, it's still too much, right, remaining. So now 64 can't go in there, but you will go into 32. So now you look at 32 and you see, okay, 32, yes, can go in there. There would be remaining, and that becomes a 1. Then you go into 16. Can 16 go in there? Um, Not really, because it's still low, right? And then obviously that goes out. And then the last one is 8, which obviously goes in there, and that will have that. Then the remainder becomes 0. So that's kind of how you kind of work out the binary to decimal. It gets easy if you understand the table, because now basically what you do is you then obviously look at adding 128 here, that's a 0. So then your next one will be 32, and then the last one will be 8, and then you add that all up, and then you would obviously get to 168. So that's kind of how you have to work out the binary to decimal conversion. But you need to use this power table, which is the base 2, to do that. Now routers does this automatically. They have to figure out how to do this using binary, which is obviously how information flows from the physical cable. And so what they have to do is they basically will understand there's a network portion and there's a host portion, which is obviously the network portion is this, and the host portion is this side here. And this is how you do your subnetting also later on. So what it will do is it will look at the network, sorry, and it will look at the IP address that you want to send the packet to. So in this case, it's 10.1, right? And it will take that IP address, put it in decimal, sorry, in binary. And so here you will see it all in binary. And because the host is 1, it will be 1 there, which is the host binary. And then it will take the subnet mask, which is class C, which we'll go through now. It will take that subnet mask and put all the ones there for the subnet mask and the host. So that will be this amount here, 255, 255, 255, because it added up all the ones. And if you add up all the ones and you work it into conversion, you will get 255. So that's like a broadcast address normally in networking. And so what will happen now is that the router will then do its AND operation, right? Yesterday we spoke about AND and TOR, sorry, and OR. So the router will look at and it will try to work out what would the network portion be. So and then it will now know actually to which network that that IP address belong to. So we'll look one in one becomes one, and we'll go through that and we'll do this whole AND operation. At the end of the day, the value that you see here is determined which is the IP there, which is the IP address, the subnet mask, and then it obviously tries to figure out now what is the network that this belongs to by doing an AND operation. 0 and 1 can't be 1, so obviously we'll make that a 0 and so forth. So next I'll just show you how does this work. So what you do is basically you take the one that's here on the host IP, and you take the subnet mask and you do an AND operation. So that will obviously become 1, that will become 1, that will become 0, that will be 0, that will be 0, sorry, 0. So there's all zeros, right? And if you add it all up, you get to 192, right? Same here, you do the same, you go through that portion. But now, when we look at understanding what network this might be on, or subnet, you basically now have to go through the whole process, and you'll basically see, that there is already 1 and 1, so that's a 1. The rest you can see is all zeros, and that is a 0, and that's a 1. And that's a 0. So if you add this up here, that will be 8 plus 2, which gives you the 10 here, right? So that's the network. That's how you work it out. Now, if you look at the host portion, again, that is 1. So you just basically use that table as your guidance to work out how you work out the network segment. And that really determines how subnetting, not subnetting, how the router thinks, looking at the binary and then converting it to decimal. So what we've done now in the trace route, we've done the following, which is actually decimal, and now that gets converted to binary. And the router sees this all in binary and not in decimal. So it's like the matrix. Okay, so moving on, you would have different classes, and the different classes is how you would classify certain networks. So you have a class A, class B, and a class C. The common one we normally use is class C for testing. And class B and A is also internal. B is normally and C is normally for internet access, depending on the range. So we would use the 192 to a certain range, and then the 128 to a certain range, and then 0 to 127 for class A. And so these are just showing you in detail how you look at classes, and the network also determines that based on how you want the classes to work. Now, when we look at IP addresses, we have two type of IP addresses. We have public, which is what the Internet Corporation for Assigned Names and Numbers assign, which is ICANN, and they assign this unique public IP addresses that we can access on the internet. So you have to kind of purchase this IP address range or the block in order to be publicly available on the internet as an ISP. And that's basically the guys that assigns an IP address to your ISPs so that they can give it to you and you pay the ISP to use the IP address. Then there's private IP addresses, which is more internal. Those are normally the testing IP addresses that you would use, like the 192 that we're using now here, and so forth. And these are just internally, they can't route on the internet or you can't ping them. You need to do network address translation, which is this here. Okay. So you can't reach them internally. You need to do a netting. And the netting basically is that you take the 192 and then the service provider converts the gateway to the public IP. So the gateway, which is the router gateway here, would then give this IP address, and people would see the IP address of the router as almost like that's the client where the information is coming from. And that is the net part, network address translation. It allows you to use the private network to connect to the internet. Now, normally you would see this if you had to do, let me just see if I have VirtualBox. I think I had VirtualBox previously. Just to show you, um, see if I'm open. I don't know why I can't see my screen at the bottom. There we go. Right, so let's see if I open up VirtualBox for you. So just to give you an idea of what netting is. So there's VirtualBox. And so with VirtualBox, you can see I've got this little VM here set up, which is not really going to run. But basically what it allows me to do is I can go into the network, into settings, and I can go into network and do the netting. So here's the net. So what it will mean is that this particular internal IP address that we have for this particular machine will then be netted, and means it will have a public IP on the outside. So you would see the gateway, which is my network, as the network for that particular device. So how you look at it also, just give you another example. Let me just use another example, which will be VMware Fusion. And so VMware Fusion, again, I have a Windows 11 virtual machine running. And so if I go to the settings of this virtual machine, you'll see the network adapter here is netted, meaning that I might have internal IP, but it will use my router's gateway to give this VM access to the network. And that's basically how you do netting. You can do bridge if you want to have a bunch of VMs all bridge together through that, or you can do host only, which means you internal, you can't get out to the internet. And so that is how you would look at how you use the network. So this means that this particular VM, although it's a virtual machine, it can access the internet because I've done the network address translation. So that is just giving you an idea of how you can do netting also and how it really works in practical terms. Okay, so when we look at special IP addresses, there's also special IP addresses out there. There's the broadcast address that I said, that's all ones, and that normally you use only allowed to use this if you want to broadcast to all the devices on your network. And that could sometimes be blocked on the network because it ends up sending a message to all the devices. It's almost like a attack you're doing, like a ping attack or something. And so again, they tend to block these broadcast addresses on the network. Any address is also another thing you can do. You can send to anybody, and that's when you do the any address. So it's all zeros, means you can send to any address on the network. And in the loopback is your local IP of your device or your PC. Link local, this you get when you fail to get a DHCP IP from a DHCP server. Then you get this particular IP. And that's also just example of different IP addresses. Now, when we look at the network itself, you have in this example 192.168.10, and that's 000 means that's the network. So that's the network range for the host. And if you want to broadcast, and that's the host side, you make it all once. Then the host that's on the 10 VLAN, they all will get the same message. That's because it's being broadcast, all once. So it's all the available hosts. But when you look at doing networking and you want to work out the usable host and the broadcast, you basically have to use this kind of notation. So you say 2 to the power of n, which is the total, minus 2. And what it means is that it will subtract the broadcast out of the equation, and it will subtract the subnet mask also out of the equation, I believe. No, not the subnet mask, the first broadcast, and then the gateway. Yeah, so we'll do that. And then the available address that will be on the network will be this one, which will be the first usable IP address on the network, because of the subtraction of taking the broadcast address and the network address. You need to take that away because you can't use those two as part of the VLSM or birch subnetting. Right. So now when we look at IP address calculation, you have the following where you have this particular IP, which is a 172.16, and then you have a kind of subnet borrowing here because you can see there's a class B. So this here ends here, right? So that is the network portion, and this is the host portion. So it's a class B because we've now basically took only two 255 and 255, and then that will become 0. So that's a subnet mask because that's class B. That's why I showed you the subnet mask before and the networks. And so in this case here, if you now need to work out a network address, you do your AND operation. So this is where you want to work out. Now you don't have to do this. Well, the router does all of this on its own. But it does this AND operation, which is AND, and it takes 1 and 1 becomes 1, 0 and 1 becomes 0, 1 and 1, 1, 0 and 1, 0, 1 and 1, 1, 1 and 1, 1. And so it goes through this whole process to work out a network address. It will stop there because remember it's a class B, it's not a class C, so it will go not going there. So it will stop there and we'll know, oh, that's the network address. From that, it will take the network address just as is and it will add all ones to the host portion, which will then become the broadcast address. And with that, it will know, oh, so the first usable IP, I now know what that would be, and I will know what is the last usable IP. The last usable IP shouldn't be the broadcast. Sorry, it will be the IP before the broadcast. So it will be 254. In this case, if you look at this octet here, and then that will be how you would then work out the calculations, and that's how the router really figures out how to calculate um, the network address and the broadcast address by doing the AND operation on this IP address and the subnet mask. So it takes these two values, right? And it works out that values in binary, and then it can know what's the network address and what's the broadcast address. And that is how the routers really see what's happening on the network using binary conversion. So also you can see the usual IP addresses on the slash 6 to the power of 16, which is the the class B IP address network, and you can see also here the available IPs on that network. So you have that amount of devices available that will use that IP, and so because of that, you could basically now waste a lot of IPs because you can see here, sorry, 255, that's basically your network, which means that you're going to have 255 different networks. That can be too much sometimes because you don't want to have so much networks. You might want to, do some subnetting from that particular 255. And so this is where we lean towards subnetting. So then subnetting comes in play and it says, oh, I just need to use so many hosts for that particular subnet. I only have 4 servers, so I'll just want to use all those subnets available. And so what we'll do is we'll take, like in this case, a class C IP address to 201.222.5.0. And now what they're trying is they're trying to assume there's 20 subnets required for the subnet, and then each subnet must contain only 5 hosts. So they will basically then take, from the host and then do the division. Basically take, in this case, if that is 5, which is the network, so they'll take from the network and they'll try to do this. Now this is the note, the sigil or the notation, and what it means that it says that I'm taking from a class C and I'm giving to the host portion. And then what it means that where your class C normally slash 24, it becomes a slash 29. And then what it means, let me just go back. What it means is that, because this is the basics now, basically, they're not giving you more context. But what this means is that if you have your subnet mask, so let's say I have 255, sorry, that should be 255. Let me just undo that. So you have 255 and you have 255 and then you have 255 and you have 0. That's your normal standard class C subnet mask. And now what you want to do is you convert it obviously all to ones. So you will have 1, 2, 3, 4, 5, 6, 7, 8. So there's your first octet. 1, 2, 3, 4, 5, 6, 7, 8. Your second one. 1, 2, 3, 4, 5, 6, 7, 8. And that's all zeros, right? So that becomes all zeros because that's now your subnet. Now, when you add this all up, that will be 8 plus 8 plus 8, which gives you a slash 24, right? So that's the notation you see here. But now, what they're assuming here is slash 29. So it means that you have to now take from the host portion and add to that. So you then will basically will have, if that's 24, 26, 27, 28, 29. And it will just stop there. And then obviously that will now be the 4 that you're now borrowing from the host, right? So you're adding that up. That's not right. There should be 1 unless it starts with 0. Let's say 20, I forgot, 25, 26, 27, 28, 29. There should be a 1 more. There's it. So there's it. Right, so that should be 5. And then what will happen is that the remainder of this will be the host. So in this case here, when you look at this here, there will be like 4 zeros remaining for the host portion. The network will be the 29, right? So all the 29 ones, and that will be the host. So you can only create, if that all goes up to in binary, you would then go start like this. So that's 1. So let's say 1, that's 1, that's 2, because you're adding up. So that will be a 1 value, that will be a 2. And now if you get to 3, you basically have to say, now while I'm doing this, remember you have this table that I spoke to you about earlier, which is 8, 4, 2, 1. This is just part of that long table. So you basically now say if you want 3, and it's 0, 0, 1, 1. So that's basically how you look at it from giving the host an IP. So the 0.1, which is just 0.1, but on the network, it will be 201.222.5. And then we need to work out, it's actually not 5, this is 5. Yeah, actually 255.255.503. Yeah, but then you have your slash 29, which now says that you've borrowed from the host. So you can then create different subnets then based on that. So you can see here, there's a 5, and then here you can see there's a 5 also, there's a 5 there also, but they will change from the host and they will borrow from the host. And that's how they do subnetting. Now that's just roughly to explain to you how they got to the 29. And that basically is, you now have to add it up, and then you will know obviously how you've bought it. So you basically took from the host to give back to the network so that you have less hosts on the network. And that's basically subnetting. I'm supposed to just give you the brief overview of it, not too much. But again, that is basically how you would do subnetting. So when we look at network basics, you have the following. You have your data that you want to send from host A to host B. And so in this case, you have two type of networks. You have your host here that sends and download files from a server, and this is a PC that just sends files to the another PC. And here you have an example where you have three devices and a router on a network, and this device wants to send data to that device there. So the router have to make sure that that gateway is allowed to forward traffic there. So this is kind of how you look at the network from a concept of the router. The router could be a switch also in this case. In this case, it's just an example of a router. Now, that analogy leads to this analogy where you have, when you look at sending parcels over the internet or to a courier service, you have to first have the information of the item you want to send it to. So you basically have to know where you're going to send this to, and that normally is the data, right? So that's the data you want to send. But then, in order to package it, right, the distribution center needs to package it. It needs to know what is the destination address. So it needs to know the destination address. It needs to know many other things that will go there. It probably needs to know the port. It needs to know a lot of things. It needs to know also the source, also a source where it's coming from. So the source address. And so those are information that needs to be fed into this package when it gets packaged. And that's the encapsulation that I'm talking about, where you have a packet, the data is still there, but you have these little headers there in front per layer. And so what will happen is that it will package all that information in there, send it to the router. The router will then obviously be acting as a distribution center and distribute all that information that it have in its headers. It will go to the internet. The internet then will obviously see and do its trace route kind of thing that I showed you earlier, and then figure out what is the next route it needs to go to, because there could be many routers here sitting. This is just one example. And then the internet will know which distribution center it needs to go to, based on the source destination address, the IP address, and many other things that's listed there. Then, after that, it will now basically do its whole de-encapsulation by removing this header here. So that will be removed because now it knows where it needs to go to. So then you can open your package and then you would see the item inside, and then you only see data. So that's how information gets transferred using this kind of analogy, where you have everything packaged into a container and it has the receiver's name, the address where it needs to go to, and then obviously the routers will have that all that headers in their conversation as they forward and send information over the internet. Now you've seen the router act as a gateway. So the gateway basically is your PC sending something to that router there. You could be a home router, and then that particular port, where the router needs to go to go out to the internet, that will be your gateway. So in this case, the gateway is set as 192.168.1.1, which would be your particular piece in this case. But then the next hop will be obviously going to the internet. So if you look at this one here, the gateway here is 2.1, which means that the PC could have a different IP address, but that would be the gateway where it needs to go out. Your PC here could be 192.168.1.10. Could be 1.10. But then it needs to know that 1.1 here on the router configured is always the gateway. So that needs to go out through that gateway to get to the internet. And that's how information flows from gateways. Right. So that's basically just a way of how it passes through the gateway. And without the gateway, you won't be able to get to the internet. So that's why the gateway is very important. And sometimes you have to configure it on the routers and switches. Right, so let's look at the following, which is basically an architecture of a communication network. And so here you would see, as I mentioned earlier, maybe in a scenario where they've done some VLSM, where you have three different offices here, and there's also a Wi-Fi access point here. So that's an AP, an access point, because you can see the Wi-Fi. And this is a switch. So these are switches, and this is a core switch, or maybe not a core switch, an aggregation switch, but we'll get to that. So that's a switch, and this is a router or core router, and this is the firewall. So what you see basically is just all different components of the network all working together. Your switches could have switches where you connect to your different networks, labs or office space in this case, and that then connects to another router, which is called the aggregation router, or a router that, not a router, or switch that basically forwards the traffic to the core network. But that route is configured that it has links leading towards all the different switches. So if there's a communication break in one of the cables, there's always a backup. So that's how they designed this kind of setup. And in most cases, this is a good setup because you want to make sure that your devices, if one goes down, there's always a backup. Right. So what is a switch? A switch is basically, the closest to your device. It isolates broadcast domains. What it means by that is your PC could forward a packet to that PC there. That becomes a broadcast domain. But with the switch there, it controls how and which packet goes to that particular PC. And so it does its whole thing about broadcasting unknown packets to find what is the next MAC address you're trying to send the packet to. And then also you basically have a MAC address table that you would use to learn what's the next neighbor or host. And they basically then the switch then forwards the packet based on what's in the MAC address table. So if we look at, I think, an example earlier, see if I can open up that again. which was this part here. Let's clear my screen. So for instance, let's say you want to do an ARP. Now ARP is basically a request you're trying to do, address resolution protocol. And normally switches does that by default. They do that. In security, you will learn that that gets done basically on the notion of trying to do ARP spoofing, right? The bad guys does that. But so if I do ARP A, I basically just see what is my neighboring networks that I'm connected to. So currently here, I'm trying to see this IP, which is the broadcast IP of this particular network, which in this case is a bridge. And then I have an IP here 192.168.8.1, which is my router's IP. So that's my gateway. So there's my gateway configured, and that's the physical MAC address on the gateway, which then obviously now I know at least it's connected on this MAC address table. Now this table will allow my router to act as a switch and actually know where it needs to forward packets that needs to go to the internet and so forth, or what needs to happen on the network. So that's basically how you can check, your broadcast and your MAC address table using an ARP. So you just do an ARP, or you do A, depending on how you want to look at it, and then it will tell you basically what's all the devices connected. And when you look at another setup, this is now a router, and the router I showed you earlier, that with a router you have, also for information you want to follow. But what the router does, it isolates your broadcast stops. Your switch isolate collision domains, which is collisions you don't want to have amongst the PCs or the network. So that's a domain. And so what the router does, it plays in between those two, and it creates this whole thing of isolating broadcast storms. So you can't broadcast, the switch can't broadcast to another switch because the router's in between there. Because the switch like to broadcast all these MAC address tables. And so that's basically what you see there. And so again, what the router also does is it acts as obviously the gateway, so it does the network address translation, and it also connects your layer 2 switches. So the router is normally a layer 3 device, and then the switch is normally a layer 2 device. So these are all layer 2s. And then your PC can be any layers, because remember you can get up to getting to the website that you want to see on your PC. Right, so now that we've known and see basically the two approaches, what are the differences between layer 2, which is a layer 2 switch, and a router? And because they're both used for the connection, right, for the network connection. So I can say basically from a layer 2 perspective, which is the switch basically just works on the MAC address. So it just uses the MAC address. The switch also does broadcasting and all that stuff, but I mean, that's a switch, it works with the MAC. If you look at a router that's layer 3, which is a router, it works only with IPs. So it only works with IP addressing, and that's the difference basically in the scenarios. The switch works on MAC addresses, and the router works with IP addresses, and that's basically how the two operate. Now, when you look at firewall is basically just there to protect your network. So you could have a firewall set up for the scenario where in this case you have a demarcated zone, or DMZ, which is a demilitarized zone, sorry, which is basically a zone where you would let the users to access files, which is probably on the internet, and then the firewall protect, whatever happens on this DMZ network, so that it doesn't get to your internal network, which is your trust zone. Right, so that's just basically to give you an idea of how does that work with regards to that. Then you have the next part, which is now, I think I'll do this before we take a break, because I've been talking a lot here. So the next one is understanding what the OSI model is and how data encapsulation work. Now, when you look at the OSI reference model, right, it has the 7 layers that we know that how network works and how information gets flown over the internet. So it has the physical layer, which is your cable medium, the data link layer, which is for your switches, and what they do is they encapsulate all the packets into frames or vice versa. It also has error checking. And then you have a network layer, which looks at your logical addresses and then transfers from source to destinations. So they use IP addresses. And then you have a transport layer, which is to do with transport. So that will use TCP or UDP. Right, so that's your transport layer. And then your session layer and the presentation layer, those are just what you can see on application. Like I showed you now, this terminal. Terminal is also part of that particular layers. And that basically allows your ports and that to operate on the application side. So this is just basically giving you an overview of the OSI reference model. And if you ever have played with Wireshark, so I'm going to just show you Wireshark. I must just be mindful that this is the introduction and the basics and not go too in depth. So I just want to check. Um, okay, why can't I open Wireshark? Wait, let's do this. Okay, there we go. Right, so let's open up Wireshark. So Wireshark is a tool that you can use to check your network and to see what's happening on your network. So currently here I've got Wireshark open. And so I can now see I'm on the Wi-Fi. So I will just do a double click on Wi-Fi and there it will show me all my packets happening on my network. Now, because we're using this particular application, which is similar to Zoom, you can see predominantly the traffic that it uses for live streaming is UDP. So they already you've known what's going on in your network. That they're using UDP to send traffic, and how you can actually see my screen is using the UDP traffic. Now, if I stop this, that shows you basically that I could reach to layer 4. Okay, so if I double click on this, it shows me more information. It shows me the data that was sent, the small data. It shows me the frame, which I think if you look at it from the top, it's a frame which is at the data link layer and the Ethernet 2. Those are what happens on layer 2, right? So you can see the destination is the MAC address of the router and the source is probably the Apple interface or something. But that's how it reads interprets these values. And then you will see IP, the Internet Protocol, which is next in layer 3. So there you can see the source and destination IP address, where this needs to go to. So the source is my gateway, 8.8.8.108, and then the destination is wherever this is going through, which I think is the Huawei cloud server for, running this live stream. And not live stream, this we meeting. And then you will see above that you have user datagram. That tells you a transport layer is UDP. And so that's basically the source destination port randomly, and then destination port randomly also getting there. And then lastly, you would see the data, which is always the same. It's just the data that gets sent across the packet. So it all gets broken down into that particular amount. And that's your OSI reference model to layer 4 that I showed you now. So transport layer deals with segments. So they have segments that they break down into smaller pieces. And the network layer deals with IPs, or the PDU, like the datagram. So it's a PDU, protocol data unit. And in the data link layer deals with your MAC address, or it deals with frames. So it sends frames also, as you saw now in that Wireshark packet. So those are, the OSI reference model. Now, when you look at the reference model, you can always compare it with the TCP/IP model. So there's a TCP/IP model, and so again, you can see in similar, they are the same. However, the standard TCP/IP model had combined these two layers to call it data link layer, and it also combined these three layers to call it application layer. The rest are all the same, right? And also, when you look at a TCP equivalent model, also the same. They combine the three top, but they've kept, I think, data link and physical link layer together. All right, so that is the reference model of how networking works, OSI. Now, I think let's take a break now. Then we can start at 11 with this, because this is now going to explain to you in data encapsulation on the network, how it works, and how you would encapsulate information and traffic. So let's take our break quickly till 11, 10 minutes, and then we continue with this. Now, before we take a break, let's do the attendance quickly. I'm just gonna, maybe if I should just cut the recording also in smaller pieces, then it's also easier for you to watch, and I just call it parts. because otherwise this will just gonna code continue. So let me just stop sharing, and stop the recording, and then we just take